All right, so without further delay, because almost 50 odd people are already there, so let us quickly start off with the session. We have the lessons on basic electronics. So if you remember on last day's class, we had already discussed a very important topic in the form of the diode current and how the current is actually, uh, I would say, physically we can understand about it. And that was given by the two basic state of current. One was the drift current, and the other one was the. Can anyone tell me what was the other current?
Diffusion current.
Diffusion current, correct. So both drift and diffusion, both of these two current primarily contributes to the nature of the total current that is going to have in case of a diode. And that led to our discussion on two different parameters. That is, drift current was primarily attributed due to the supply voltage, that how we are defining the supply voltage, and based on that, we were calculating the both the hole as well as the electron, what is called that electron. Both electron and hole pair constitutes the two drift currents specifically, and also the electron and hole concentration. In fact, that also keeps a fact. It becomes a factor when we consider the drift current. On the other hand, when we are looking at the diffusion current, it was primarily with respect to the concentration gradient that is changing with respect to PN junction diode, where we are leading from one, we are moving from one space, one position to another, and as we are moving towards the junction, the concentration will come down, and eventually we found out that there was a negative symbol that was indicated. I'm not writing anything because I'm hoping that all of you have gone through the materials that I've uploaded. It is there already. So in that way, you can find out that both the total current was a part of both the drift and the diffusion current. So based on that, some of the very similar kind of based on that understanding, we actually can solve questions and numericals also on top of it. Although usually the questions that we come across, some of the questions I have already solved. I have told you in the class itself, where we had actually we have found out the expression for conductivity, we have found out the resistivity. I have in fact given you one question to solve and give me the answer, for which unfortunately I only took, I think, Swam, I think he has sent me a message. Jigme, I think he also had sent me one of the message, but not others. I don't know why you have not done any of the assignment that I've given you. At least you could have tried doing it and try to find out that whether the answers are correct or not. But anyway, I don't have the time to go back to those again. So hopefully all of you will be in a position to at least answer similar kind of question. So talking about those similar kind of question, let us do a very small little simple question, or like a different type, I would say. So let me just start sharing my screen. All right, so this is a very similar, this is a different type, I would say, but this is also kind of calculating the current and cross a diode and all. And this will be in fact helpful when you are doing the same or similar kind of experiment or the assignment when you are doing for task 2. Okay, very similar kind of questions you will expect. So the question is something like this, or question can be of this type, that for example, this is a circuit provided to us. So I would want all of you to pay attention to this. So suppose I have a circuit which looks something like this, right? We have two diodes here and we have two diodes over here. All right, so this is the configuration that we are looking at, and we name it as D1, D2, D3, and D4. All right, and we have a supply voltage of 10 volts. Okay, now the question is, and in between this, in this part, we have a resistance in between. All right, so this is my R, and R is given by 48 ohms, suppose. All right. Now the question is that calculate the current through this 48 ohm resistor or the R that we have mentioned in the circuit shown. All right. Now given the supply over here, and also it's mentioned that the nature of the diode is silicon. All right. And it has a breakdown voltage VB. We call it the breakdown voltage. Hopefully all of you by now all understood what is breakdown voltage. The voltage after which the conductivity or the diode starts to conduct. So this VB is around 0.7 volt. All right. And the forward resistance, okay, forward resistance, which is the resistance offered by the diode, which is very small actually, that is given by 1 ohm. Okay. So this is not someone's mic is on. Can you switch it off? All right, so this is suppose given provided to us. So the question is to find out what is the current which is flowing across this R, okay, and that is based on this configuration. Now, if you're given a circuit like this or any of this nature, because usually it's applicative type for the from the understanding, you should understand and answer the question. So you can observe you very carefully that whenever the supply voltage is 10 volt, you can observe that the D1 and D3, okay, ideally these two are in forward bias condition. You can observe that this is positive, so maybe the current is passing like this. So this path is what it is following. I'm just trying to draw with other color. So like this, because this part D2 and D4, you can see that ideally they are reverse biased condition. Based on the supply, they are all in a reverse bias condition. Hence, this will be an open circuit for the same. So the circuit would look something like very similar, like it's just the equivalent one. It will look something like this. It is a path through a resistance, and this path is existing. All right, and this is the overall circuit, whereas the other part will be something like an open circuit. Here also there will be a kind of an open circuit. All right, so this is the type of circuit we are virtually visualizing. So ideally what is happening, this is positive, so the supply is this is positive and the current flows on this particular direction. All right, so this D1 and D3 are active diodes, whereas D2 and D4 are the inactive diode because they are reverse bias condition. All right, so please take this into account that while calculating this sort of questions. So from very clearly you can observe that the net total circuit current, if I sorry, not the current but the voltage, we have to calculate the current later. Total voltage if I consider, so that will be, please remember this carefully, 10 volt is the supply, right? 10 volt is the supply we have provided. So this 10 volt is supposed to have that should have been the output voltage as well. But as we have two diodes and the two diodes both has a particular breakdown voltage as well. So while we are calculating the total net voltage across the circuit, we have to have 10 minus 0.7 and minus 0.7 because one of this has come from D1. The other one has come from the D3. So as the current is passing through all these two diodes, there will be two drops which we need to consider. So please make a note that whenever you are trying to calculate the entire voltage, you have to consider the breakdown voltage. Only if suppose in this question, it was mentioned that consider the diodes to be ideal in nature. Okay, this particular word, ideal in nature. If that was a word, then we could have considered that the potential, that VF that you're talking about, that we can we would have actually ignored. The breakdown voltage we would have ignored, or even the internal resistance as a forward resistance, that can also be ignored if at all it is called as an ideal diode. But ideally that won't be the case. Naturally there will be it will be a non-ideal diode, you can say, and that's why there will be some amount of breakdown voltage that you need to consider. So please consider this 0.7 and 0.7 over here. So the net value is getting around 8.6 volt. All right. Now, if this is a net voltage, now the total circuit resistance, if I calculate, that will also be taken care of with respect to the diode. So the total resistance is nothing but 1 ohm over here for this D1, 1 ohm over here for the D3, and the 48 ohm which we already had. So the total resistance is 1 plus 48 plus 1, which is 50 ohm. All right. So the internal diode forward resistance have also been considered while this particular net circuit current is established. So the total current, if I consider, will nothing be 8.6 divided by 50, and that will be around 172 milliamps. All right, so this is a very similar. This kind of questions are very common for diode analysis, and you can readily use them for your understanding and for necessary calculation. In fact, as I said, this can be also proven with respect to the simulation platform. Also, you can drop in the values and you can check that what is the net result, whether we are observing or not. The procedure I already told you in lab, so the same thing you can also do it to test. All right. So this is one of such question for it. Anyone having any doubt why we are doing this, or what is the pattern? Because I'm trying to give you the different patterns of questions that you might expect out of it. So any doubt with this kind of question? Simple only, right? It's not that, just the assumption is important.
Yes, sir.
That whether you understood the concept of forward bias and reverse bias. So keep that. If yes, sir, is the answer, can someone quickly do this particular question and tell me the answer? So we have a supply voltage like this, suppose, and it has 20, I'm mentioning is as 24 volt, and we have a 2k ohm over here. All right, and we have a circuit which looks something like this. All right, and we have a supply voltage again over here. All right, so this is grounded. This is also grounded. This is E2, and this is given by 4 volt. And we have two diode D1 and D2 present over here. 2k ohms there. The question is find the current I. Question is find the current I. Okay, that is a circuit current. Assuming this is important, the diode to be silicon type and RF, which is the forward resistance. We just now had mentioned forward resistance, which is equal to 0. So this is the given question for us. So can anyone quickly do and tell me what is the value of I you are getting and how you are getting it?
The breakdown will be 0.7 only, or is it ideal?
No, silicon, if it is 0.7 only. So if I consider, since of lack of time, I need to finish up other portion also. I'll just let you know what exactly we are trying to do. So in this case also, you can observe that this D1 is basically a forward biased condition, whereas D2 is in a reverse bias condition. All right, so that's why what will happen that the circuit element or the circuit current will flow through D1, instead nothing will come through D2. All right, since it's a reverse bias condition. So ideally, the circuit current will be the combination, the net resultant voltage E1 minus E2 minus breakdown voltage divided by the total resistance which you are offering to, which is 2k. All right, because why it is 2k? Because the internal resistance is supposed to be 0. So that's why we have considered it to be 0. Only 2k is existing. And this one, you can observe, this is nothing but the difference in potential when you are applying two different voltage sources. So that's the resultant voltage source that we are getting. Got it? So this is 24 minus 4 minus 0.7 divided by 2k ohm. And that gives us a value of 9.65 milliamps of current. So similar kind of questions you can expect. You can just go on doing it as and when it is required, and you can find out a right solution. Also, you will find that I will upload a few more questions similar to this so that the doubt gets cleared. All right. So I cannot extend much of the numericals even after this. So let me go back to the presentation and let us quickly finish off the remaining portion that we are supposed to do. Let us finish off everything and then I'll come back once again to discuss a few more points. So what we have done up till now, the forward bias, the reverse bias, the breakdown voltage, the barrier potential, depletion region, the diode current equation, the junction potential. So all these elements are absolutely crucial for your understanding. So please go through the materials and whatever we have finished so far. Now, based on that, we can define also some of these parameters which are essential for a diode. One of the cases maximum forward current. All right, that is IF, the forward bias. Whenever you are making a diode to be forward bias, after a high, it's the highest instantaneous forward current that a diode can conduct without damaging to the device itself. This device part is missing over here. So without damaging the device, whatever the maximum forward current you are supposed to get. So you can remember that we had a VI characteristics. Now both the batches, since you have done the experiment, so it was something like this, right? So this is basically I, F, and this is my voltage that we are applying. So this maximum forward current is the highest instantaneous current that can be conducted for a particular diode. It depends naturally, it depends on the different type of diode and their material, and based on that there will be a specific specification after which the diode might get burned out. So that's one of the parameters that we can find out, or rather it's a specification, it's a product specification you can say. The other important thing is called as peak inverse voltage, or in short we call it the PIV. Now PIV is the maximum reverse voltage that can be applied to the diode without damaging it. This in fact will be very useful later on when we discuss about the Zener diode or the process that is involved with reverse biasing condition. But anyway, for the time being, you just remember that it is the maximum reverse voltage that can be applied to the diode. Without damaging it means that, as we know that in reverse bias, when we are considering the reverse bias condition, we are giving the power supply or the voltage source, there will be very least current at some point. But after you will find that in Zener diode, what happens that for a specific type of diode, after a certain period, there will be a huge breakdown and there will be a huge rush of current that will take place. I'll just show you the diagram maybe. I'll just have a diagram somewhere here. So this, if you see, this is called a Zener breakdown. I'll come to that if time permits. So this is the huge drop in the current as if it's a symmetrical to the forward bias region. Remember, this graph only we had generated in lab, right? So in the same way, in the Zener part, you can see there is a huge drop in the voltage, drop in the current we are experiencing, but for very less change in the voltage. So anyway, that is another point of discussion. So why I told you this, because this is basically gives us the peak inverse voltage for that. Another last point is called as the maximum power rating. So it is again the maximum power dissipated at the junction without damaging it. The power dissipated at the junction is equal to the product of junction current and the voltage across the junction. So that's the power, like I square R as we know, or V multiplied by I if we consider. So that's how it is. Okay, so junction potential you have already calculated. Similarly, junction current can also be calculated, and we can find out what is the maximum power rating. These are specifications to diode, so we don't need to worry much. Now comes to the application part of diode. Why we are studying this? And one of the most important activities that a diode will have is called as the rectifier. Already I told you some part in lab also that whenever it is the cheapest and the most efficient circuit that converts an AC to DC. And now you imagine that most of your household devices, or in lab equipment, or for any supply for that matter, we all are having an AC supply. So in some way or the other, if you want to operate the device that you are operating with a constant velocity, so not constant, with a constant amplitude, then definitely you have to convert the AC to a DC. And that is where a small circuit of this diode is absolutely essential. So you can see that the first line, as it indicates, AC power is easily produced in bulk in bulk form through different methods. But many power control circuits and industrial applications that runs are on DC power. So that is the main issue. We have to conscious that how somehow we have to convert AC to DC, and the rectifier is the easiest way to do it. Already I showed you this graph in one of your batches. I think in both the batches, I think I have shown this. So if you observe carefully, it's very simple to understand. So HWR stands for half wave rectifier, and this is called as full wave rectifier. So this nomenclature I will be using at some point of time, so you can just also keep a track of it. Now, in case of a half wave rectifier, in the left hand side, what you are observing that we are applying a sinusoidal voltage. Remember, in lab also I showed you that how the sinusoidal voltage we are going to apply in the LT spice. So here also you can see that the voltage, the supply voltage is a sinusoid. All right, and as it is a sinusoid, definitely it will have a positive cycle or a negative cycle. All right. Now, when this is passed through this diode, what happens that this positive half or the positive supply, when it comes over here in this diode end, definitely it is a forward bias condition. So during the positive half cycle, positive peak, if I consider the shaded portion, okay, there will be an output at the end of RL. So across the load, RL is called as a load resistance. Okay, it's called as load resistance. So across the load resistance, you will get the output as desired. But what happens in the opposite direction, that whenever there is a negative peak over here, the negative peak will make sure that this diode is reverse biased, because it's a negative half, and negative won't be allowed by the PN junction diode or the diode for that matter. And what will happen? So the negative part of it will be completely eliminated. You can see here, it's a flat line we are observing. All right, so this will continue for the overall duration, and so in a way what we are observing in this half wave rectification, that we are actually getting a constant output. If you observe this dotted line, and if you take the magnitude of this, okay, if you take the magnitude of this is constant throughout. So as if I take all the peak value that is coming, okay, all the peak values, those will be coming, that actually if I add up will be nothing but ideally a constant DC supply. All right, so this is basically what the principle of a half wave rectification is. But naturally, it has its own problem, and that can be solved by the full wave rectifier. So let's see, first of all, what is half wave rectification and its properties. So you can see that during the positive half cycle of the input, the diode D, okay, conducts as it is forward biased. All right, and hence output is observed across RL. Whereas when it is negative cycle, hence there is no output that is observed. Now, this in what we have discussed over here up till this point, we can solve it. Okay, we can solve it in two different ways. What one of the ways that we can opt for, that how we are doing this rectification, is using a transformer over here. You can see the transformer present over here. This is also a half wave circuit, but it is called as a step up transformer based rectification process. All right, so this is a transformer that you are looking at, this primary, secondary. So this is block. Okay, this block that you are looking at, this is a transformer we are using. Now, why there is a transformer over here? Okay, let me just check if there is. We'll see the full wave. Let it be. So why there is a transformer over here? Okay, one of the reason for it, please make a note of it. It's not mentioned. I've just kept it as a question for all of you. I was hoping that you might you might ask me like why we are using a transformer over here instead of only directly giving the supply over here, just like here. So the difference between the left hand diagram and the right hand side diagram is that we are adding a transformer over here. The first of the reason for this is, first reason is that it is a, if it is a transformer, then the step down, step up or step down the AC supply. Okay, so if there is any anomaly is observed in the input, that can be controlled quite easily with respect to the transformer. So that is one of the reasons. So sudden high or sudden low of the AC supply can be controlled using the transformer. That's one. And secondly, if anything goes wrong, the rectifier circuit is isolated from the power supply. Because see, this is my power supply, right? AC input. So if anything goes wrong here, the transformer maximally will get defect. and it will save all the device which is connected over here. That is in fact one of the reasons why you will find that most of your household, you will find that if you go out of your house and you will find that nearby there will be a transformer somewhere in your locality, and that transformer actually does the same thing. That whenever from the power grid the supply is coming, the transformer will step up or step down the voltage, and based on that it will be fed through the line to your house. Now your devices which are mounted, whatever be the equipment, electronic equipment you are using, those are safe, because if anything goes wrong with the power supply, the transformer first will get burned out. All right, so in fact to avoid that, in fact you will find that in most of our household purpose there will be a fuse connected to it. So that fuse might also get burned out to save the equipment. So those are the reason why those fuse, those part are important, right? So this same thing happens over here. The transformer is used in order to make this thing happen. All right. So this is about the some like alteration to the half wave rectification. But it is observed. You can clearly observe over here that one of the major drawback of this system is that while the negative part is completely eliminated over here, the information or whatever the data we are looking at with respect to this negative cycle, that is also lost. Like instead, we can say in fact that this is basically half of the, it is working as a half efficient system, because the total value of the AC, if you observe, so this is my total amplitude. If you consider the total positive and a negative cycle, so this is plus minus 5 volt. But here you are restricting it to a small little 5 volt. So you are reducing it as far as the amplitude also is concerned. So it is not a right solution. So you are actually generating an efficient, your rectification efficiency. If we calculate, we'll do that. You will find out that that will come around only 40%. So you are feeding in 100% of AC input. You are getting only 40% of the output. So basically 60% of your generation is completely lost. Understood. So in that way, the process of half wave rectification is not a very good solution. All right. So let me just finish off with the full wave. Then I'll come back to half wave once again with the calculation. So in order to avoid that, anyone having doubt till this point, like any problem, anyone having question on this half wave rectification till now?
Excuse me, sir. Can you explain the first point why there is a transformer?
Nothing else. Its transformer is, see, in the left hand side, if you are looking at the left hand circuit over here, there is a power supply. Okay, and eventually the power supply is connecting to the diode directly. So if any anomaly happens over here in the power supply, that will definitely damage the diode as well as the load resistance. This RL, remember, this RL is nothing but, you can imagine it to be an equipment. Any equipment will have a resistance. So its RL is actually indicating that device, suppose. So any damage in the supply will damage the device itself, courtesy this diode. All right. So to avoid that, if I am adding one in between a transformer over here, so this transformers, the basic role of a transformer is, see the term transformer. So it transforms one form to another. So what does it do? It will, if there is a huge AC voltage, suppose there's a high spike, suddenly there's a spike that has come in. Okay, because of the AC generation, some fault has happened and there's a high spike. So that will damage the circuit if there is no transformer. Transformer is like a buffer. It will just hold it from getting damaged, or the whole circuit. So what I mentioned over here is that the step up and down process of the AC voltage will help in making sure that there is no damage done to the end circuit. Understood? So that is why the transformers are used. Clear?
Yes, sir. Thank you, sir. I understand.
Thank you. Okay. So this is about the, so, and then the problem, as I stated, that the efficiency of half wave rectification is only around 40%. So you are sending 100% of a data and you are getting 40% out of it. It is not a very good system. It's not a very good solution, to be honest. So I need a better solution to make sure that at least I would generate about 80% of its efficiency. All right. So that is done by the full wave rectification process. So if you observe here in this particular example, this is a full wave rectification. All right, so what is exactly full wave opposite to half wave? It's basically if we design a system such that there are two half wave connected together, then we are assuming that one part of the half wave will work for one cycle and the second part of the circuit will work for the second half cycle. Then it will be fine. That will be okay. So you can see that here what happens that we are adding up two such diode over here. Okay, so this is called as center tapping full wave rectification circuit. All right, so in this case, the transformer is still there, but there is a center tapping over here. Center tapping is usually used. Okay, it's usually used to make these two halves equal. Okay, and there is some other applications of it as well, but that is not of your concern as of now. But so current flows through the load in the same direction for both the half cycles. Okay, so you can see that here what is happening, that this is my positive cycle. So this part will be conducting and this will be reverse bias, because you can observe clearly that it is something like this is positive, this is negative, because this cycle has come in like this. So suppose I have the supply, so this plus sign, this part has now appearing over here. So after transformation, so this is positive and this is negative. So what will happen? This positive will allow the current to flow like this, only this top half cycle. Whereas this is negative and this diode is connected like this, so there will be no connection, no current which will be flowing through it. So for the very first half, you are supposed to get an output which will look something like this, which is the same as that of this, right? Or you can see it here. So this is suppose the first output. Now what happens in the second half, when this negative cycle will come in, this polarity will change. That means this will be my negative and this will be my positive. And as this is my positive, this positive will make D2 as a conducting diode and D1 as a non-conducting diode. So now the output which you're observing is through this RL once again, and it is going throughout this. So if you're taking output over now, so the D2 diode is responsible for getting the second set of. So you can observe that whatever happens, if the sinusoid is present for each positive and negative half cycle, there is a uniformity in the way it is being generated one after the other. So you can see clearly that the output, if you're observing, so this is my first cycle, this is my second, this is my third, there is fourth. So you can see that this part, if I shade it to red, this part was missing in half wave rectification, which has been added in a full wave rectification process. All right, so this is one of the advantages of having a full wave rectification. On the other hand, what happens, you can see, observe over here clearly that in this particular, the left hand side diagram, there is an error, that there is a problem with this. And the problem is that when we are considering the center tapping, okay, this center tapping or finding the center tap is very, very difficult. This is what is mentioned over here. Positive half cycle of input, end A is positive. See the diagram. This is only I had drawn previously. So this part is only working. All right, end A is working. So this is A and B is negative. See, this is B, this is negative. Okay, so D1 conducts and D2 is cut off. So D1 is conducting, D2 is cut off. Whereas when a negative cycle of input comes in, the end B is positive and A is negative. So D2 conducts and D1 cut off. Okay, so DC is obtained across RL. So RL is over here. Okay, while the current across RL is in the same direction for both the half cycles. So it's basically two half wave rectifier clubbed in together. Okay, so the output you are observing, this is 1, this is 2, like that. And by center tapping, the impedance of the two halves of the windings are made equal so that they look symmetrical. That's the only thing. But to find out the right point at which this impedance will match, that becomes a real tough job. It's not a very easy solution, actually. Although in perfect, like in theory, it is possible, but in practice, the center tapping transformer is very difficult. Okay, to avoid such a thing, okay, we usually look into the next part, which is called as a bridge rectifier. But before I go to bridge rectifier, is there any doubt with the center tapping forward full wave rectification? Anyone? Half wave rectification, all of you have understood, I guess, that whenever we have a diode and the diode is allowed to have some cycle AC supply, and the AC supply based on the positive and the negative half, there will be ideally the diode will act as a forward bias or a reverse bias. When there is a forward bias, it will allow the output to happen. When it is reverse bias, it won't allow to happen. So if you are looking at a conventional half wave rectification, only 40% of the efficiency is obtained, which we will compute. Maybe next day we will compute that, or maybe I'll take it some other day. But on the other hand, so that is not a very efficient solution. So in order to get that efficient solution, we need a center tap forward, a center tap or a bridge rectification based full wave rectification. Whereas what we are observing, that we are dividing the circuit into two half wave rectification, and the transformer that we are using in between, that also makes sure that there is an impedance matching for both the circuits. So as if both the circuits are symmetrical, they are kind of mimicking together. All right, and for one half cycle of the supply, there is one diode which is conducting, whereas for the second half of the cycle, the second diode is conducting when the other diode is switched off. So that is being explained over here. Any doubt with the center tap?
Sir,
yeah, please.
In the last, for the half wave rectifier, you said that it had 40% efficiency.
Yes.
So does a full wave rectifier have 100% or less than 100%?
80%, almost 80.26. We'll compute that. We'll compute
really
that.
Double.
Yes, almost the double. Okay, but it can't go to 90s and all. Even that can be achieved. To be honest, if I tell you, that can also be achieved using a capacitance in between parallel to the load resistance. Usually, this RF that you're looking at, no, there is a capacitance that is added to it. What does the capacitance do? If time permits, I would have shown you, but there is very little time actually devoted for this topic. So what will I might show you in the lab itself. What it will do is that if the capacitance is placed parallel to the diode or the load resistance, what will happen that during a positive half cycle, the capacitance will charge, right? And after in the negative half cycle, it will start to discharge. And this charging and discharging will make sure that the supply that the output that you are getting is very near. So it will look something like this. I'll just show you the diagram. Like I don't have the diagram right now.
It compensates for any losses that
that is in fact called as something called as ripple factor. We'll see that. So this is basically what happens. This is how the capacitance charges. Just it's an off topic for the time being. Charges and then it starts to discharge. Okay, it will start to discharge like this. After a certain period, by the time it is completely discharged, it will again start to charge like this. Again, it will start to discharge. So if you take this peak values, no, and if you neglect this negative discharging part, because capacitance.
So
we might get an output which will almost look something like this. This part is DC. Understood? So that will happen.
Repeat what you said just before your voice cut off.
Okay, I was saying
we can ignore the discharge.
When the capacitance is charging and there is a discharge, so charging is what we are more bothered with, because the capacitance is supposed to store charges. All right, so that is where we focus on. If we only focus on the charging part only, we can prove that by increasing the capacitance value, we might get an output which will look something like this, the one that I've drawn over here. So you can observe that this is a constant supply. This is a constant DC that you're getting. So the efficiency that I was talking about, 80%, that is somehow increased to almost around 85% to 90% based on the capacitance being used. But if it is a pure circuit like this, it will be around 80%.
Okay. Thank you, sir.
Thanks. So this is about the center tap. But as I said, there's a problem. So that is reduced very much in this bridge rectifier circuit for full wave. You can observe it's a very nice illustration also. I think all of you must agree to this. So you can see that this is a supply. You can see that you can explain on your own. So the supply, when this supply is there, the arrangement is a little different. See the arrangement carefully. This is my D1, okay? This is my D2, this is my D3, and this is my D4. So what is happening? You can observe that whenever we are, suppose on a for a particular case, say check here. When it is positive, see the direction in which it's coming. I'll just stop it for the time being. Let me just stop it, okay? To explain. So this is my supply. This is my positive. So what is happening? This is positive. This is negative. So as it is positive, the diode which is D1 is now forward biased because this is plus, this is minus. So it goes here, okay, at this junction. Then it comes this side as well as this side. Now, if you observe, this is my, if suppose I mark this point as A and I mark this point as B, so towards A, it is the reverse bias condition. So nothing will flow through D4. The question that I just now had solved, I told you that this kind of a arrangement we can observe. So through D4, there is no current. Whereas this B current, if it goes like this at this node, it can go either to this direction or it might come this direction. All right, but the direction towards this green diode, you can see this is a positive again, positive minus. So both D1 and D2, it is actually a path which is shown over here like this zigzag path. So at this point, we are getting an output based on what the input was. Am I understandable here? Is it clear with this? How the flow is working? First, this is a supply. This is plus minus. For the plus supply, these D1 and D2 are forward biased and D3 and D4 are reverse biased. So no supply, no connection, nothing here, but the full supply voltage is across this D1 and D2. So we are getting an output, which is the law of forward biasing rectification process. Second half, when it is negative, when this part comes in, negative dotted line comes in, definitely the other way around. So this will be my positive and this will be my negative. So what will happen? This, if it is positive, if this supply is positive, definitely what will happen that the diode D4, okay, if I suppose remove this part, whatever we had, let me remove all this. All right, let me remove it. So you can see D4 and D3. Just look at it carefully. D4 and D3. This will be positive and D1 and D2 will be negative in the second half of the cycle. Right? And as it happens, so the second half cycle will also becoming something like this. So it is very similar to the center tap that I discussed. But the advantage is that you can see that there is no such tapping over here. So no tapping is present. No tapping is present. So the complexity regarding the tapping of the circuit is not there, which is a huge advantage. Got it? So in that way, what we can see that the rectification is done, full wave rectification is happening, but without the central tapping. So that has been mentioned over here. The DC output is small as each diode utilizes only one half of the transformer. This is basically with the previous problems that we are looking at. Here, as you can see, no center tap is required. Okay, no center tap. Output is twice that of the center tapping. Center tapping, whatever we were getting, it is much better than that. So that is why the center tap won't be used any further. PIV, or the peak inverse voltage, is one half that of the center tap circuit. The peak inverse voltage, remember the reverse current, reverse voltage after which the up to which the diode can resist. So that is also one half of that of the center tap circuit. Okay, so that's an advantage also. Output frequency, that is this frequency of the DC that is generated, that will be twice the input frequency. Suppose it is a 50 Hertz. Suppose it's a 50 Hertz signal that you have given. So the output frequency of the DC supply will be around 100 Hertz. And far better efficiency than HWR, which is a half wave rectification. The only disadvantage you might say that it requires 4 diodes instead of the 2 diodes which were present over here. Here it was 2 diodes, whereas here there are 4 diodes which we are observing. So that's the only small. So maybe the circuit may be a little bulkier. That's only option, only problem that you can address. That is basically the way the full wave and the half wave rectification works, or the application of one of the very important application of diode is used. Let me see the time a little bit. What is the time? Can anyone tell me? 47, right? You have a class, 1 second, right? I would have just, can I take 2 minutes to finish off the Zener diode also? Just 2 minutes?
Yes, sir.
Yes, sir.
Just then whole thing will be finished actually. It will be a complete thing. So the other application of diode that we come across is called as the Zener diode or a voltage rectification. We call this a voltage rectification. Very simple because you already know the process, so it won't be taking long. So voltage, I would say not rectification, but I would say voltage stabilizing. That is a correct word actually. So that is this is called this is done by something of a special this is regulation, voltage regulation I would say. Okay, and that is done by a specific set of diode which is called a Zener diode. Now Zener diode is ideally a same diode, very similar, same diode which you are using, except that it's a high doped semiconductor. I have already told you the Zener avalanche breakdown, the Zener breakdown that I was talking about, that after a certain period, the depletion region will break the minority carriers and there will be a huge rush of current. So here what happens if you are having, see the symbol, okay, this is a very conventional symbol. The normal diode is looking something like this. Here, this is bend over here. That's the only difference. And in fact, when a Zener diode is acted in a, please make a note also, that when it is used in a forward bias condition, it is same as that of a normal diode. No change. Normal. This is C. This is the part. This IV characteristic, if you observe, this part, the forward bias region, is same as that of the normal diode. The interesting part comes in a reverse bias condition. When you are applying a reverse bias condition for Zener diode, what happens after initially there will be a very small current. See, the voltage is changing over here. Reverse bias voltage, negative voltage. The current is very small in microamps. It is coming till this point. After a certain period, somewhere over here, which is called as the knee voltage or the breakdown voltage, you can say that as a breakdown voltage also, you can observe that there is a huge current that is coming in. Almost very similar to the forward bias condition. It's a huge current that is coming in. And this is what we called as a Zener breakdown voltage. So for reverse bias, initially there will be a small current of microamps. Then at a certain value, the reverse current increases rapidly and sharply. Right. So what is the significance? You can observe that there is a huge change in current. You can observe that this particular zone, if you observe, there's a huge change in current that has happened, but the voltage is ideally constant. Can you observe this? Is a huge change in the current. Any increase in the reverse source voltage, any increase, because see here the source is the power supply. All of you agree that, right? The power supply. So the power supply is supplying the negative voltage, right? Now suppose there is an anomaly to the source where there is a huge current coming in from the source and you want to restrict it. So if you have a Zener diode, what will happen that after a certain period, after the knee voltage is reached, even if the current is more, there will be hardly any change. This will be constant. There will be hardly any change in the voltage. So thus it avoids any damage to the device due to excessive heating or any other purpose. So you can see the circuit diagram. Same way, this is plus. So this is my minus, this is my plus. So this is a reverse bias condition. Remember in Zener diode, only diode which has a function with respect to reverse biasing condition. This is a special type of diode which is highly doped, which has the Zener breakdown, which we have already discussed earlier. And due to the Zener breakdown, what happens that there is a Zener breakdown region that is formed. And the context and the consequence is that with increasing in current, there is hardly any change in the voltage. Hence, we can use it as a voltage regulator. So let us stop it at this point. Thank you very much for your patience hearing and all. I've already overshoot. I think I have intruded to the other class as well. Please tell me. Please go ahead.